Example number 2. They ask us design the digital control with the CZ, KZ plus AZ plus B such that the dominant closed loop pole are Z star minus 0.25. That means here they give us the Z star. The previous example, we must calculate the Z star based on the specification. The parameter A will be chosen to cancel about the unstable pole of the plant. That means A can select such as the cancel about the one of the pole unstable pole. If you see the pole here, one of them around 0.5, another one is minus 1.2 is here unstable. I choose the A, the cancel about the unstable pole. Okay, then if you write the CZ GP, because CZ equal to Z plus A Z plus B multiplied by K, I choose the A is 1.2 and the GZ for me is Z minus 1 and Z plus 2. Here Z plus A and will cancel out, and simplify the equation will be this. Based on the two rule of the root that arctangent Z plus B, that means dominator is equal to minus arctangent pole plus minus 180. That means become sum of the angular about the pole minus sum of the angular about the 0 equal to plus minus 180 degrees. Here do have it become theta, for example B. Here I put the theta 1 plus theta 1. Here I don't have any 0, will become 0 is equal to plus minus 180 degrees. That means theta B equal to 180 degrees minus theta A. That means if I find the theta A, then I can find the theta B, then I can find the B. For the K, if you remember the K, GZ, CZ should be equal to 1, and here is a Z star. I can find the K here. First of all, I know the Z star. I connect to the all of the pole I have. One of the pole I have is 0.5. Then I calculate the theta A. Theta A, then I can calculate about the theta B. Theta B will equal to 33.69. If I put the approximately B here, will be theta become bigger than the 90 degrees. That means B should be close to here. Now I know this angle is 33.69. Arctangent is become this distance. I know 0.5 divided by this distance. This distance, that means B minus this become this distance. I can find the B easily. B minus here and 0.5, I can find a B equal to 1. Okay, I find the B then easily by the GZ, HZ, here HZ the CZ, and absolute value of this multiplied by K will be equal to 1. I can find the K. Then the CZ become K. I put the A 1.2 and I find the B equal to 1. Another method, you can use the analytical method to find the B and the K, and if you see the B and the K in analytical method exactly become the same as the B and the K in the root system. Here they draw the system with the discrete time will be come here and start to will be stable. Assuming that the unstable pole of the plant is not exactly known, and here becomes z plus 1.201, but the control is still the same as the I put the z plus win, and after that there is not expect pole cancellations. If they don't cancel, you will see your system start to be diverged. That means if you have a CZ the same as the before, that means K, Z plus A and Z plus B, and you have an unstable pole, this one they cannot cancel about the unstable pole in the system. Your system will start to become diverged even you have a controller. Another thing, they cancel the stable pole. Now I want to cancel about the stable pole, because in the system, if you remember GAP, you have the one of them S minus 0.5, another one S plus 1.2. Now I want to cancel about this. For cancel about this, the same method, we will find the A, this, and you find the B by the root, and you find the K by the second rule of the Lucas. Then you will find the B is 0.51, and if you draw the system, you will see the system start to become stable. Now here we have some rules. The control CZ should only cancel the stable zero and stable pole of the planet, otherwise an infinity small error on the pole or zero will lead the closed loop become unstable that we saw together. If CZ cannot cancel about the unstable of the pole, your system will start even with the controller will be start then become diverged. This is the rule that you should learn. Now we go to frequency response, general system. Here after the any system with the input magnitude of the MI and the phase of the Phi go to any system, the output become the change in magnitude and the phase become the Phi O. The output frequency is the same as the input frequency, only the magnitude will be changed. The amplitude and phase of the signal have the change and the dip on the depend on the omega. Okay, this one we saw in the E312. If you see, the phase will shift, but the frequency all the time is the same. For example, if this is the input, output can shift forward and backward, can magnitude increase or decrease, but the frequency about the system, that means the omega in the input and output, is the same. Here should I give the example. The input is a blue line and the output is a red. You see the magnitude change and the phase the shift, but the frequency is the same. Here another example, the magnitude decreased and here is the shifting. If I put the system M omega Ts E J phi omega Ts, all the time magnitude about the system will become magnitude output divided by magnitude input, and the phase by the system become the phase of the output minus the phase about the input. M omega Ts is a magnitude frequency about my system, and the phi is called phase frequency response, and the M omega Ts E J phi omega is a frequency response of my system. Frequency response in the system, if you remember, you put the S go to the J omega. In the Z plan, the frequency appear as Z equal to E J omega Ts, because if you remember Z equal to E S TS, in the frequency domain, that means S should be go to J omega, in the Z domain become E J omega TS. And it is not possible to use the logarithm property to add the asymptotes body diagrams. To overcome this difficulty, we can use the binary transfer function about the omega equal to 2 ts z minus 1 z plus 1. That means if you have a S-plan, by this transfer function, they go to the Z-plan. That means the left half of the plan, all of this point, by this transfer function go inside the circle. And inside the circle, again, by the omega z minus z plus 1 2 ts, they go to the S-plan. That means from S-plan, by this transfer function ESAT, I go to the Z-plan, as from the Z-plan by the omega equal to 2 ts z minus 1 z plus 1, I go to the omega plan or S-plan. We can apply the usual frequency method in the omega plan, Nyquist, and the body diagrams. That means if you have in the Z, you change the Z to the W plan and you implement the Nyquist and the body exactly the same as in your S plan. Be careful about the distortion about the V equal to 2 ts tangent to omega ts divided by 2. A frequency pre-wrapping can be done in order to limit this distortions. If the bandwidth frequency is omega b, then the system will be designed for the VA b equal to 2 ts tangent to omega b ts2. This one, with the one example, become more clear. Digital control are the nonlinear continuous controllers. In this part, we will see the zero steady state error with no ripple after a finite time. The name is a deadbeat response. The analytical method can also be used to place the pole of the closed-loop system, and we start by the TZ. The transfer function will be the controller multiplied by the GAP. Here is a CZ, and you write the closed loop about the system. If numerator here multiply denominator here, and the numerator here multiply by 1, and simplify and find the CZ based on the TZ and GZ, we find the CZ is equal to 1 open about the GZ, TZ 1 minus TZ. Now we would like to see the constraint on the prototype TZ, such as the casualty. We will see the fast transient or overshoot, the name is a pole placement. Zero steady state error after finite time, the name is a deadbeat. First of all, objective to have a zero steady state error by the input about a step ramp after minimum finite time. The name is deadbeat response. To satisfy any specification for the closed loop transfer functions, the name is pole placement. Okay. Here is the deadbeat controller with the ripple they show with the blue line W3, and without the ripple is a Y2. This is the dead bit response. We talk about the dead bit response, then we go to the pole placement. Dead bit response, if we have a transfer function about the system, about the equation about the z in numerator and z in denominator, if you simplify, you can find the TZ in the dead bit response A0 plus A1 z minus 1, etc. And all the time we know it, n should be bigger and NAP, where NAP is the order of the plant. Pole placement, denominator exactly denominator here, denominator they have a combination about the pole. PI is a desired closed loop poles. This is the two definition, dead bit and the pole placement. Casualty, the order of the nominator of controller must be equal or lower than the order of the dominator. Imagine the control system is a combination about the Q plus Q1Z and the P1 plus P1Z, and if you see the order about the nominator MSC all the time should small or equal to NC. Example, USZ equal to ESZ, 1 plus Z plus Z2, and ESZ is 1 plus Z. This is the CZ. Why CZ? Because if it's a controller here is a ESZ, here is a USZ, or the input about my plant, and here they make your system. That means the CSZ become USZ divided by ESZ. Okay, if you nominator here multiply here and denominator here multiply denominator here and simplify the equation and take the inverse of the Z, here become UK plus 1 equal to minus UK plus EK plus EK plus 1 plus EK plus 2. Here they show the nominator about the order about the nominator is bigger than the order about the dominator, and here you have the UK plus 2 will be appear as normal. Why we cannot is not the casual? Because you cannot have a pass of the EK plus 2. In order to have a order about the dominator